Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 36, Dimensional Consistency Rules. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi is changing, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, in this part of our journey, we pause again to listen carefully to just one of those echoes. Our ascent has revealed the holophase language in its majestic structure. We have seen the hierarchical backbone of constraint chains, which bind higher derivatives to lower ones, and refinement chains, which allow higher derivatives to add nuance and precision to meaning. We have climbed through wave semantics, quadratic semantics, and action principles, and we have seen how time, space, and motion are never truly separate, but three inseparable voices in a single song. But a profound question must now be answered with absolute clarity. How does this single language, describing a single field, manage to speak coherently about these three seemingly distinct realms without ever contradicting itself? How does the universe avoid splitting into three incompatible stories, one told in time, one in space, and one in motion? The answer lies in the most stringent grammatical rule of all. It is the rule that prevents the story from fracturing into separate, inconsistent tales. Today, we meet the ultimate guarantor of coherence. We explore what we will call dimensional consistency rules. This is the level where we prove that the triunity is not just a poetic idea or a philosophical image, but a hard, mathematical, and falsifiable requirement built into the very fabric of the language. It is the rule that says no dimension can go rogue. No temporal description is allowed to disagree with the spatial description of the same phenomenon. No motion description is allowed to wander off and tell a different story from the one implied by time and space. In the holophase view, the world is lawful because phi is one, and because its dimensional expressions are chained together by consistency. Let us return to the core. There is one field, phi. Everything we observe, every rhythm, every shape, every movement, is a pattern in phi or in its derivatives. Omega is not a separate time substance. It is a measure of how phi changes in time. K is not a separate space substance. It is a measure of how phi changes in space. V is not a separate motion fluid. It is a relationship built from omega and k, the way the pattern traced by phi travels through the fabric of the field. They are three readings, three projections, of the same underlying activity of the single field. This is not a loose association. It is an identity. Just as your height, your weight, and your voice are different measurements of you, omega, k, and v are different measurements of how phi is changing. Because they are measurements of the same thing, they cannot contradict each other. Your height measurement cannot tell a story that your weight measurement flatly denies, if both are accurate and you are one person. In the same way, the story told by the temporal derivatives of phi cannot contradict the story told by its spatial derivatives and remain a story about one field. They must be consistent. This necessity for consistency gives rise to specific, powerful rules, the dimensional consistency rules. These rules are not an optional extra. They are the basic logical glue that holds the entire holophase language together. These rules are not additional assumptions pasted on top of the theory. They fall out logically from the starting point of a single, differentiable field phi that is defined over space and time. They manifest in several key forms. The first form is derivative relations, often encountered as the chain rule. This is the most fundamental consistency rule. It links derivatives across dimensions. In its simplest form, for a pattern traveling along a line, the change of phi in time is related to its change in space through the speed of the pattern. In words, if a wave pattern is moving, the rate at which you see phi changing at a fixed point in time must equal the spatial steepness of the pattern multiplied by how fast that pattern is sweeping past you. If these two calculations, one obtained by watching a clock at one point and the other by looking at a snapshot across space, gave different answers for how phi is changing, then the idea of a coherent traveling pattern in a single field would collapse. A second form of dimensional consistency appears as dispersion relations. We have already met these as grammatical rules that connect omega and k. A dispersion relation omega of k is a consistency condition between time and space derivatives for a wave-like solution. It says, for a wave to exist in this medium, if you have a spatial wave number k, you must have a temporal frequency omega that is precisely this function of k. It is not a suggestion or a matter of taste. It is an equation that must be satisfied if the structure is to be a valid solution of the equations of motion. The dispersion relation ensures that the temporal oscillation you measure at a point matches the spatial pattern you see across many points, tied together by how the medium lets phi propagate. A third family of consistency rules shows up in energy-momentum balances, written in the language of quadratic tallies. Recall that omega squared is a tally of temporal intensity, and the magnitude of k squared is a tally of spatial intensity. Laws like omega squared equals c squared times k squared for light, or energy squared equals momentum squared times c squared plus mass squared times c to the fourth for particles, are consistency equations for these tallies. They say that the amount of temporal activity and the amount of spatial activity for a given entity are not independent dials you can turn freely. They are locked together by a universal conversion factor, such as the speed of light, and by intrinsic properties such as rest mass. You cannot have a massless photon with enormous temporal frequency, but practically no spatial momentum. The rules force a specific trade-off. In each case, time and space are being forced to tell the same story about what kind of pattern phi is forming. In the Holophase language, these dimensional consistency rules act like a metagrammar. The derivatives and equations of motion provide the basic syntax of words and sentences, but the consistency rules govern how the different dimensional perspectives can be used together to form valid statements about the world. They ensure that a sentence that is grammatically correct at the level of differential equations is also logically coherent at the level of the full tridimensional meaning. A law that seemed to work when only time was considered, but failed when looked at in space, would not be accepted. The metagrammar demands a deeper coherence. To appreciate the power of these rules, imagine a world where they are violated. Let us construct an ungrammatical physical scenario. Suppose we have a pure wave in a uniform medium. We measure it carefully in two ways. From the time perspective, we sit at one point and count oscillations. We determine that the wave has a frequency of 100 cycles per second. From the space perspective, we take an instantaneous snapshot and measure the distance between wave crests. We determine that the wavelength is 1 meter. Now we ask what speed this wave should have. From the time measurement, if the medium is air with a speed of sound of 340 meters per second, we would expect the wavelength to be 3.4 meters. From the spatial measurement, using the same speed of sound, we would expect the frequency to be 340 cycles per second. We have a glaring inconsistency. The temporal story and the spatial story are telling us two different things about what kind of wave this is. If such contradictions were real and not just measurement errors, they would imply that the pattern we see in space is not the pattern that is evolving in time. The field phi would be behaving as if it were two unrelated fields, one governing spatial shapes, another governing temporal rhythms. There could be no such thing as a consistent wave speed. The very concept of a traveling coherent pattern would break down. Communication via signals would become impossible, because the structure you send would not be the structure that arrives. This is the kind of nonsense that dimensional consistency rules simply forbid. They enforce that the temporal and spatial descriptions must be different views of the same object, and therefore must be mutually predictable. Consistency is not a luxury in a physical theory. It is part of what we mean when we say something is a physical theory at all. A proposal that allows contradictions of the kind we just described is not a description of reality. It is a description of confusion. In the Holophase framework, consistency is non-negotiable for three deep reasons. First, it arises directly from the premise of a single field. You cannot start from the claim that there is one phi and then permit its time description and space description to disagree about what it is doing. The premise itself contains the seed of consistency. Second, consistency is required for falsifiability. A theory that is internally inconsistent can be made to predict anything after the fact, because it is not tightly constrained. It cannot be decisively tested. The consistency rules sharpen the holophase language, forcing it to make hard predictions that can be checked. Third, consistency reflects the empirical reality of a coherent universe. We live in a world where signals propagate and repeatable experiments are possible. This observed coherence is direct evidence that the underlying language of reality obeys strict dimensional consistency rules. These rules enforce harmony across the three echoes, in every observable phenomenon. In the time echo, consistency means that the frequency you measure must be compatible with the history of the pattern. If you observe a process that repeats every second, then any spatial pattern associated with that process must evolve in a way that respects that 1 second cycle. You cannot have a temporal rhythm of 1 second and a spatial pattern that implies a completely different effective frequency in the same medium. The temporal narrative sets a constraint that the spatial narrative must obey. In the space echo, consistency means that the shape you map must be compatible with how the field is changing in time. If you map an electromagnetic field and find a particular pattern of curls and divergences, Maxwell's equations tell you exactly how that field must be changing in time to remain a valid solution. The spatial snapshot contains, through the consistency rules, information about its possible past and future. In the motion echo, consistency comes most vividly to life. The trajectory of an object is the living proof that the temporal and spatial stories are in agreement. A parabolic arc is the only path where, at every instant, the object's vertical position and its vertical velocity and acceleration satisfy the constant acceleration equations. If the motion were to suddenly depart from the path required by these relationships, the time-based and space-based descriptions would no longer match. The object would no longer be a solution of the equations of motion. The motion we actually see is therefore the embodied agreement between the time echo, the space echo, and the motion echo. Within the structure of this episode, Part 36 serves as a kind of structural capstone for the whole chapter on hierarchy and recursion, and as a reinforcement of the tridimensional theme that has run through all of Episode 7. After exploring how derivatives build upon each other vertically through constraint and refinement, we now see the horizontal guarantee that cross-checks those vertical towers. The dimensional consistency rules ensure that the elaborate structure built in the time tower is the same structure described in the space tower and manifested in the motion tower. This is what makes the language unified rather than fragmented. These rules also connect tightly to all the neighboring branches of the holophase tree. At the level of the core alphabet, they are literally the relationships between omega k and v. They define the group velocity as d omega by dk for wave packets and enforce dispersion relations omega of k. At the level of constraint chains, those chains are primarily vertical within a given dimension. Dimensional consistency rules are horizontal, tying together chains across dimensions. Together, they form a rigid, interlocking grid that confines possible phi patterns to a highly structured manifold. At the level of the action principle, the action is the generator of the primary consistency rules for a given system. When you derive equations of motion from an action, you are deriving the specific dimensional consistency rules that fields in that system must obey. At the level of falsifiability, this node is the epicenter, a clear, reproducible violation of an established dimensional consistency rule in a well-understood domain would strike at the heart of the framework. At the semantic level, the meaning of dimensional consistency rules is that they represent the dimension of coherent existence. To exist as a physical entity in the holophase sense is not just to occupy a place or to endure for a time. It is to be a pattern of phi that successfully satisfies the consistency rules across time, space, and motion. It is to be a solution of the governing equations that binds these three perspectives together. An entity that violated these rules would be a phantom, something that might appear in an image but could not move coherently, or something that might flash in time but could never be placed anywhere in space. We do not admit such phantoms into the shared fabric of reality. The consistency rules, therefore, act as the border between the infinite space of mathematical possibilities and the much smaller, coherent subspace of actualized possibilities, the stories that actually get told. Because these rules are so central, they are constantly being tested. Every time we study a propagating phenomenon, we are effectively checking dimensional consistency. In optics, measuring the frequency of laser light and its wavelength, and finding that their product yields the speed of light, is an everyday practical test of omega equals c times k. In quantum mechanics, the de Broglie relation that links momentum to k and the Planck relation that links energy to omega together enforce a consistency between spatial interference patterns and temporal energy measurements. In general relativity, the consistency between gravitational time dilation and spatial curvature around massive objects is a subtle but precisely tested aspect of how time, space, and motion are connected. In each case, time measurements, space measurements, and motion inferences lock together according to rules that can be written and checked. To see even more clearly how demanding these rules are, it helps to look at the idea of stability and variability from their perspective. A pattern that satisfies all relevant dimensional consistency rules is in a state of dynamic coherence. Its temporal rhythm, its spatial structure, and its motion through the medium all support each other rather than fighting. When a wave packet travels through a fiber without changing shape, or when a planet orbits a star in a nearly closed path for millions of years, what you are really seeing is a long-term success story of dimensional consistency. Time, space, and motion are in ongoing agreement. By contrast, when patterns break apart, blow up, or fade, it is often because small inconsistencies are being amplified. In turbulence, for example, the basic consistency rules still hold, but tiny variations in initial conditions are stretched and folded by the dynamics, so that a configuration that was almost self-agreeing in all three echoes ceases to be so on larger scales. The system remains mathematically consistent, but semantically, it becomes very hard to find persistent, simple stories that remain true across time, space, and motion. In this sense, stability and instability are about how kindly or how harshly the consistency rules treat small deviations. There is also an important distinction between local and global consistency. Locally, at each point in space and instant in time, the derivatives of phi must satisfy the exact differential identities that come from calculus and from the action principle. Globally, when we integrate these patterns across large regions and long times, we obtain conservation laws and integral relations that must also be satisfied. A familiar example is energy conservation. Locally, the energy density and energy flux of a field must satisfy a continuity equation, which is itself a dimensional consistency rule tying time change to spatial flow. Globally, when we integrate over all space, this becomes the statement that the total energy is constant in time. A field configuration that appeared to create energy from nowhere or make it disappear without flow would be globally inconsistent and therefore unphysical. Once again, phi is permitted enormous freedom to form patterns, but it is never permitted to break the web of consistency that ties all its expressions together. Because these rules live at the intersection of mathematics and experiment, they are also the most direct way to falsify or refine our models of phi. When a new physical phenomenon is discovered, scientists do not just try to fit its time evolution or its spatial profile separately. They test whether there exists a single dispersion relation, a single set of consistency equations that can connect all the observed aspects into one coherent story. If no such link can be found, and if the data is robust, this signals that our current action, our current supposed description of phi, is incomplete or wrong. The search for new physics is essentially the search for the correct, deeper dimensional consistency rules that govern a wider range of patterns than we previously realized. We also see this logic outside physics, whenever we ask different kinds of evidence to agree. Documents in time, objects in space, and measurable changes in motion, all supporting one shared story. In technology, modern systems engineering is built around this same principle. An autonomous drone, for example, fuses information from cameras, gyroscopes, accelerometers, barometers, and GPS. The software does not treat these as independent streams. It constantly checks whether the drone's estimated path through space, its measured accelerations in time, and the visual flow of the landscape are all consistent with a single underlying motion. When they are not, the system flags an error or enters a safe mode. The code is, in effect, implementing a miniature holophase logic. Do all dimensional views agree about what is happening? Even in personal life, we apply an intuitive version of these rules when we judge integrity. Someone's words form a story in time. Their actions shape a trail in space. The way they move through challenges expresses a kind of moral motion. When these three line up, we call that person authentic or coherent. When they speak nobly but act destructively, or when their promises and their behavior diverge, we sense a dimensional inconsistency in their being. They no longer feel like one field, one phi. Our discomfort arises from the same deep expectation that a true pattern, whether physical or human, should tell a single consistent story from all angles. Seen from this perspective, the dimensional consistency rules are not abstract technicalities. They are the formal, sharpened version of a demand that runs through every layer of our experience. That what is real must be self-agreeing when viewed in different ways. Holophase simply extends this intuition to the deepest level, where the underlying field, its derivatives, and the action principle together determine which patterns qualify as physically real and which remain mere fantasy. In practical scientific work, these rules show up as cross-checks and calibration procedures. Before trusting a new sensor, we compare its time series with the spatial map produced by a more established method. Before accepting an astronomical measurement, we check it against independent estimates from orbital dynamics or spectral analysis. Every such cross-check is a miniature experiment in dimensional consistency. When they succeed, they strengthen our confidence that we are truly reading phi rather than fooling ourselves with artifacts. When they fail, they point us toward deeper questions and sometimes toward revolutionary revisions of the action that we believe governs the field. By bringing all of this into the explicit language of holophase, we gain not only a unifying picture of existing physics, but also a disciplined way to search for its extensions. Any proposed modification must still honor the bedrock requirement that the one field, phi, produce time, space, and motion stories that fit together. This gives us a clear lens for evaluating speculative ideas. No matter how imaginative a new proposal is, if it breaks dimensional consistency in a fundamental, testable way, it cannot be a description of the world we inhabit. You can cultivate an intuition for dimensional consistency by looking for hidden connections between what you see, what you hear, and what you infer about movement. Watch a shadow move across the ground as the sun sets. The spatial change in the shadow's length is tied to the temporal change in the sun's angle by the Earth's rotation and by simple geometry. Listen to a car passing by and feel how the pitch you hear encodes information about its speed and direction relative to you. Push a child on a swing and notice that if you try to push at the wrong time, out of phase with the swing's natural period, your effort fights rather than amplifies the motion. In each of these cases, you are, perhaps without realizing it, respecting or violating a dimensional consistency rule. Finally, we return once more to the one field, phi, and to the complete holophase tree. The dimensional consistency rules are the ultimate expression of phi's unity. The tree of derivatives, with its chains of constraint and refinement, grows upward from phi. The consistency rules are like interwoven strands that tie all the branches together, ensuring that the whole structure grows as one living organism rather than as a patchwork of unrelated parts. With them in place, we can now see the holophase not only as a field and not only as a language, but as a single coherent thought unfolding through time, space, and motion without ever contradicting itself. As we stand at this vantage point, we are ready to turn to a new question. Which phi patterns are able to persist as meaningful sentences, and which ones quickly disintegrate like noise? In part 37, we will explore semantic stability versus instability. We will look at stable and unstable configurations, the role of derivative chains and balances in stability, examples from orbits, waves, turbulence, and chaos, and the semantic interpretation of lasting nouns versus fleeting noises in the holophase language. This will bring together many of the letters and rules we have learned into the notion of stable expressions that endure across time, space, and motion. Salam, and peace be upon you.